Good day, guys. You're welcome to Techland. Now, today we are going to resume our class on 24-volt inverter, which was suspended due to some personal technical reasons. So, in today's class, we will begin with the feedback, which was where we stopped. We are going to design the feedback in two manners. We are going to use the analog feedback, and then we are also going to design it using the microcontrollers. So without wasting your time, let's move to the guys. This is the board from where we left it. I know it looks a little bit different from where we all left it. I'm going to explain why the new development. Now, unlike the normal inverters, our feedback is going to use it input a negative signal from the two transistor bank, that's the left and the right. That's where it's going to use to sense the decrease or increase in the inputs in order to properly adjust the output of the inverter to match the load and maintain stable output voltage. So that's why we needed to include the power MOSFET, which will drive the transformer, and then some other filtering capacitors, which are in the previous class I talked about it as the final filtering that occurs between the two outputs of the left and right power MOSFET channel, and then some other couple of resistors and diodes, which will be explained in the design process. You guys, I'm done with the design. This is the design. I've done with the placement of the voltage regulator, 15 volt regulator. So let's arrange everything so we can start the design of the feedback. I'm going to use a project board so I will be able to make corrections before moving it to a permanent Vero board or PCB. So as you can see, there are outputs here, which are an extension output, which I'm going to use on the breadboard in order to design the circuit. The two outputs here goes to the transistor base, the two bank of the transistor, the base of the two transistor bank, and then this is the output. This one is the output from the power transistor, that's the total output of the two bank, which is passed through a diode, so there won't be a reverse current. And then we have power outputs. We have the 15 volt outputs, and then we have the ground. I'm going to connect all of them to the breadboard, and from there our design begins. So the very first thing, I'm going to power up the circuit by connecting it to a 24 volt output. The circuit is on, operating at 57 Hz. That's the frequency of operation, 57 Hz. Let's analyze the circuit so we know what we need to design the feedback. Now, what we want in this circuit is to be able to maintain a stable output voltage on the transformer aspect. And unlike the normal feedback, the feedback in this particular design senses its inputs, its negative feedback input from the output of the two transistor bank that are driving the transformer. So what we need is a NOT gate. And how does a NOT gate operate? Now, whenever an inverter transformer is being wound, it's wound to give a very high voltage if supplied with the respective maximum voltage that is being designed for. For example, a 12 volt transformer might give up to about 300 to 400 volts of output if supplied directly with 12 volts or full power. So what the feedback circuit does is this: at no load or minimum load, it adjusts the base of the transistor down to a point whereby it maintains a certain amount of standard voltage that is required in a certain country. For example, in Nigeria here, in which we operate between 220 volts to 244 volts. Now, the feedback at no load will adjust the output power of the power MOSFET that's supplied to the transistor down such that the transformer will give maximum of 220 volts. But now when you put a load, what happens if there was no feedback? If you put a load at that point, it will subtract a voltage, leaving nothing. So at the end, you have reduction in voltage instead of maintaining the voltage or adding a little bit voltage on top of the existing voltage. So what the feedback does is this: when you put a load, the load takes what it's required, and the feedback replaces what the load have taken using voltage. So at the end, you end up seeing your 220 volt irrespective of the load you put on your inverter. So that's what the feedback is responsible for. The very first thing we need, our voltages and different power outputs are in place. So we locate the base of the two transistors, which are these. Since what we need, this is a MOSFET, an N-channel MOSFET, so it means it requires a positive charge at the base to turn on or to allow communication between the source and the drain. So what we need is a PNP transistor, bipolar transistor, PNP bipolar transistor. The transistor I'm using is A733. So base the base of the individual transistor bank are connected to the collector of the A733. Now, what we are going to do here is to allow communication between the flow of positive charge between the base of the true bank of transistor and the positive output from the 15-volt regulator. So there can be a flow of positive charge within the base and the power source. And then the next part is to separate the base of the transistor using an high ohms resistor. In this case, we are going to be using 1000 ohms resistor, in other words known as 1k ohms. The reason for this is transistors are not always working the way they should when their base is being directly connected in such occasions. There will be a leakage between the base of each other. That's the collector, sorry, the collector of each transistor. There will be a leakage between the collector and the base, which might allow one of them stay stable or and the other unstable. So because of this, we use a resistor to indirectly isolate both base, creating a resistance, a high resistance between the two transistors. After doing this, the next thing is to directly connect the emitter of the two transistors together, which will then feed from the 15 volts, positive 15-volt output. So then we connect it to the 15-volt output. Then before we proceed, one of the things we need to do is to add an LED indicator. Now this LED would show us if the feedback is giving an high output in respect to the amount of load at the output of the inverter. We're going to run a partial test by directly absorbing power from the output of the MOSFET to see if the NOT gate will increase the base uh, charge in order to allow the inverter carry more load and maintain a stable output voltage. So this is a white LED. I'm going to plug it. I'm going to connect the negative pin of the LED to the output of the two bank transistor bank, which is this cable here. And then I'm going to add a resistor in order to, you know what a resistor does, to at least reduce the power, output power to LED, knowing that LED uses a very small amount of power to operate. So from the positive, I'm going to connect the resistor to the positive 15 volt outputs. Okay. Now that we have connected the two transistor to the base of the transistor, to the base of the power transistor, the next thing is to, this is the output, the two outputs of the NOT gate. So the next thing is to work on the input of the NOT gate. At the input of the NOT gate, we need the same PNP A733 transistor. For this one, we connect the collector of the transistor to the positive output of the 15 volt power source. Using a 500 ohms resistor, I do not have a 500 ohms resistor, so I'm going to parallel to 1000 ohms resistor to give me 500 ohms. We connect it from the emitter of the inputs, the NOT gate input transistor, to the base of the outputs, NOT gate outputs. Not directly to the base, but through the transistors, but through the resistors which are used to isolate the base of the two transistors. So that is done. Now the next stage is to use a variable resistor. Now the reason why we use this variable resistor is that this is where we are going to be, this is what we are going to be using to adjust and set the output voltage of our inverter. Now this variable resistor, one of the pins will be connected one of the pins will be connected okay, the middle or common pin of the variable resistor will be connected to the base of the NOT gate output transistors. Remember, not directly to the base, but through the resistors that are dividing the base. And then either of left and right pin of the variable resistor will be connected to ground. I'm going to shift the ground down here. Now, as you can see, the power MOSFET output is on. The reason why it's on in full is because the NOT gate input have not yet been activated. Before we do that, let's set the variable resistor to 50k. This variable resistor is a 50k ohms variable resistor. So the next part is to use a 1k ohms resistor, connect between the base of the NOT gate input transistor and the outputs of the power MOSFET transistor. So I'm going to plug it to the output of the power MOSFET transistor. Now, as you can see, the output of the NOT gate has gone off. The LED, the white LED, indicates when the power MOSFET output is on or off. So what we are going to do here, there is always an initial power output, a low output, in order for it to use to turn on and carry out the detection. So the we are going to tune the variable resistor responsible for setting the output voltage, at least to leave the power transistor a little bit high. So as you can see, that's enough. Now what is going to happen here is that when a load is connected across the power MOSFET, the NOT gate should increase its power at the base of the MOSFET in order to be able to match the load and also maintain a stable output voltage. Using this LED, we will see the indication. So what I'm going to do is this. I'm going to use a speaker load to connect between the MOSFET bank. We are also going to hear the audio sound generated by the power MOSFET, and also see the LED increase. I'm going to just connect one pin of the speaker to positive and then use the other pin between the MOSFET outputs. On normal occasions, the transformer will indirectly link the two banks together. That's from the primary core. So you have to do that before testing. You can hear the sound and you can notice the LED here, which is responsible for indicating increase and decrease in the output of the MOSFET bank, goes high whenever I connect the loads to the output. So our NOT gate is complete. So let me further explain what happened. Now, this is the NOT gate input transistor. This transistor is responsible for sensing decrease at the output of the transistor bank. So when it senses this decrease, what it does is that it activates the two output transistors to increase the amount of power it sends to the base of the two transistors, which will in turn increase the output of the two transistors back to its initial point, which was set using this variable resistor here. For example, assuming this inverter is complete and we use this transistor to set it to a output voltage of 220 volts. Normally, in the absence of feedback, when you put a load, the voltage will drop irrespective of the power at stored in the battery. So what happens is this: when we put a load and there is a voltage drop, the feedback will automatically increase the voltage back to its initial stage or a little bit higher in order to be able to power the load and maintain a functionality of the system. That's how feedback works. So the circuit will be posted in the group. So thanks for joining this class. In our next class or in our next video, we will be winding the transformer